Today we shall look at wireless networks which are intended for usage in much smaller areas than 802.11 that we had discussed in the last class. We call such networks wireless PAN, wireless personal area network. Now, what is the basic difference between wireless personal area network and wireless LAN? They are expected to have smaller coverage area, lower data rates, and ad hoc only topology. In 802.11, we had distinguished between ad hoc as well as infrastructure based wireless LAN. In fact, I can have an infrastructure based wireless LAN where I have an access point connecting to the backbone. Here, the primary objective is to set up ad hoc networks. And the more important thing in this context is of lower power consumptions. And that is also a reason why you would like to limit coverage over restricted area. Bluetooth is currently an accepted IEEE standard for personal area network. It has got a short range, low power consumption, uses 2.4 gigahertz, which is available. It's an unlicensed band available widely, but it interferes again with 802.11b, which also uses 2.4 gigahertz. It enables voice and data transmission at 1 Mbps rate and has got low cost. And it supports what we say open-ended list of applications. In fact, lots of application concepts have developed around the Bluetooth specifications. What are the different application scenarios? You can have data and voice access points, and through those access points you can have file transfer, you can have real-time data as well as voice transmissions. So example is 3-in-1 phone. You can have a cordless phone to base station, an intercom device as well as a cell phone. In fact, your hands-free set for a cell phone can be connected via a Bluetooth link. The original objective with which the Bluetooth was started was to replace cables, variety of cable connections which are used for short range, short distance connections, whether they can be completely eliminated. And in fact, now Bluetooth has grown beyond that very basic requirement. Also, the ad hoc networking, devices with Bluetooth radio can establish connection with another when in range. In fact, this gives a very interesting advantage that whenever you are moving around and you discover another Bluetooth enabled device, you can establish connection and an ad hoc network. The Bluetooth organization is based around two very basic concepts, that of piconets and scatternets. Piconet in a way is a cell which is a basic unit of Bluetooth networking. A piconet typically will have one master and 1 to 7 slave devices. If there are additional devices in the piconet, they will not actively participate in communication. Only the maximum of 7 slave devices can participate in communication with the master. So each piconet has got one single master. Scatternet is the next higher level, okay, which consists of a set of piconets. Devices is one piconet may exist as master or slave in another piconet, and this allows many devices to share same area and makes efficient use of bandwidth. So basically, if you look into it, this is what would be the concept of a piconet. You have got this master, these are slaves. Before a connection is created, a device is in standby mode, and it periodically listens for messages every 1.28 seconds. And then devices are connected in an ad hoc fashion when there are other devices, forming dynamically what is called a piconet. Each piconet has got one master and up to 7 slaves. The node which actually initiates a communication through negotiation typically takes over the role of the master. Other devices within the piconet which are not slave will be considered parked. This is a parked device within the piconet. It is actually synchronized with respect to the piconet. What is meant by synchronization we shall discuss later on, but it is not participating in data communication with the master. That's why we say that this node is in parked mode. These are in standby modes, okay. So they are not actually in a way part of this piconet. Parked devices as well as slaves are synchronized to the master. Then you have got scatternet. What is done in scatternet? Multiple co-located piconets are linked up through sharing of a common master or slave devices. Okay? Master in one can be slave in another piconet. A device can be slave in one piconet and master of another. No device can be master of two such piconets. So pictorially it looks something like this. These are the two overlapping piconets. Okay. This is a slave which is common between the two piconets. These masters are distinct nodes. Okay. And in fact you can see that effectively I can establish communication between these slave nodes with these slave nodes because of this common slave connecting the two. In fact, this common slave functions more like a bridge between the two piconets. So effectively what we get is interconnected piconets within the scatter net form a backbone for mobile area network. That means you can actually have a complete network consisting of a set of piconets forming scatter nets. Okay. So you have got the nodes which may not even directly communicate with each other, because keep in mind that range is, I said, about 10 meters. So there can be two nodes separated out. They cannot communicate directly with each other, but through this provisioning of piconet and scatter net, they can establish communication even though they do not have direct link. In fact, Bluetooth provides the protocol specification for point-to-point connection as well as for enabling devices not directly communicating to get linked as well. In fact, these two aspects are taken care by Bluetooth and which goes into creation of a mobile area network. What is a protocol structure? Obviously, at the lowest level, you have got a radio frequency communication. Okay. On top of that, this is specification of the physical layer. On top of that, you have got the baseband. Okay. How the basic data is to be structured, packetized, communicated. You have got a link manager. You have L2 cap. We shall discuss this later on. And on top of that, these are basically what we call middleware protocols for various applications. And these applications sit on top of these middleware protocols. And in fact, interestingly, you will find there is a specific audio protocol as part of Bluetooth which enables audio transmission. So these sits directly on top of your baseband layer. Okay. So it is not at an application level that audio is dealt with. And you have got through this control what we call host controller interface. In fact, host controller interface provides a mechanism for interfacing of a Bluetooth host with the corresponding application. We shall not go into details of these protocols, but let us try to understand these basic functionalities. In fact, we have seen from the diagram, it is again a layered protocol architecture. Okay. You have got core protocols, cable replacement and telephony control protocols, and adopted protocols. In fact, we shall come to them later on. Core protocols are what? The radio, baseband, link manager, link control and adaptation protocol, as well as service discovery protocols. What the radio protocol is supposed to do? it has to provide for the basic communication. Bluetooth is based upon spread spectrum as well as, and in spread spectrum as required, it uses frequency hopping. The baseband, it provides a link control at bit and packet level, coding, encryption, that is packetizing issues. The link manager protocol sets up the link and manages the link, and logical link control and adaptation protocol provided services to upper layer protocols. That means applications which provides a data that has to be segmented into the packets. Again, when you are receiving the packets, they to be put together. So this is the L2 CAP protocol. Okay, and in fact, you can realize that once I have at the top layer, I can have even implementation of TCP/IP protocol, which can go through your L2 CAP. So TCP/IP would be in this case a middle group protocol. In fact, middle group protocols are of a variety of form. A simple, if you remember that picture, you have got RFCOM, which is a serial port emulation protocol. Okay, so it enables legacy applications to operate seamlessly. That means when we are having a serial port connectivity and I want to emulate the serial port connectivity over radio frequency, I shall be using the RFCOM protocol. In fact, you remember we talked about a telephony control protocol. Okay, so say for example, if we consider that application where we said we have a telephone, okay, which can be moved around, which is communicating with the base using your Bluetooth. So I need a protocol to do this controlling. Okay, and we can have even a three-way telephone, a telephone as well as a cell phone. Okay, and in such a case, you need a telephony control signaling protocol. In fact, TCS is a protocol at a middle layer which provides this application. Then the more interesting thing is service discovery protocol. If you see, your Bluetooth is basically an ad hoc protocol, because if the devices come in contact, they discover each other. Now, these devices can provide various kinds of services. Now, how do you understand the services being offered? You need a protocol for service discovery. So, service discovery protocol discover available services and connects two or more devices such as fax machine, printing, etc. Okay, so it can discover a printer, it can discover a fax machine which is in the neighborhood. So that is enabled by the service discovery protocol. What is the packet format? Packet format is typically like this. You have got an access code, packet header and payload. The access code identifies the piconet, because there can be overlapping piconets forming a scatter net. So I need to know whether this message is for a particular piconet or not. So that gets identified by the access code of the packet. There are three classes of transmitters. In fact, if you can see that these three classes of transmitters basically consume different amount of power, and hence the ranges are also different. Typically, it is the most commonly used is a 10 meter range. There are other two class 1 as well as class 3 range of transmitters. So the key aspect of this Bluetooth communication, that's a physical layer part of it, is frequency hopping. What does frequency hopping mean? And why is frequency hopping used? Obvious reason for frequency hopping is to provide resistance to interference. What does frequency hopping means? That these transmitters hop from one frequency band, a narrow band set of frequencies, to another narrow band frequencies over a time period in a particular fashion. Now, these makes the system resistance to interference as well as multipath effects. What is a multipath effect? If it's a wireless protocol, your data is actually getting reflected from the environmental objects and it will again come back. So the data that is being received can come via multiple path, and that can cause interference. And I need a mechanism by which I can minimize this interference. In fact, spread spectrum communication with frequency hopping provides this capability. And that is precisely the reason why you will find the Bluetooth is using spread spectrum communication. How it works? So, it provides a form of multiple access among co-located devices in different piconets. In fact, there is a total 79 frequencies are used for hopping, okay, and each is of bandwidth 1 megahertz. So, you start with 2402 megahertz, because I said it is 2.4 gigahertz as a basic range, and you have got these K bands, which are K is shifted from 0 to 78, because we are talking about 79 such bands, and these frequencies are used for hopping. All devices in a piconet follow the same frequency hopping sequence, and they use 1600 hops per second when they are actually communicating. So, therefore, each frequency is occupied for a duration of 625 microsecond, which is called a slot. Okay. So, the communication is therefore this kind of slot centric, okay, and the frequency hopping pattern, okay, is same with respect to a piconet. So, what is the hopping sequence? Every Bluetooth device has got a unique device ID. It's a 48 bits Bluetooth address and a clock. So, master gives a device ID and clock to its slave, fine. So, the master determines the hopping pattern. So, since the master manages the piconet and a piconet has got a unique master, so each piconet has got its own hopping pattern, okay, and the timing in the hopping pattern is determined by the clock, okay. All slaves therefore synchronize to the master. In fact, what does that implies? That implies that slaves cannot transmit in a random fashion. It can only transmit in synchronization with the master. And if you remember, we talked about park nodes. What are park nodes? Park nodes are not really transmitting, but they are still synchronized with respect to the master. So, what can happen is a current slave node can be put to park state, and the current park node can become a slave, okay, and that is the basic advantage of having park nodes synchronized with respect to the master. So, how do you manage really the piconet therefore? So, when two Bluetooth devices enter into a communication range, they attempt to communicate. If no piconet is available, you need to negotiate to set up the piconet, okay. So, when you negotiate, one device will become a master and other become a slave. Typically, the device which initiates communication becomes a master. In fact, the whole protocol specification is there for this negotiation, because if you remember, I talked about the Bluetooth specification for a point-to-point communication. So, this is between one slave, one master. If I negotiate, or there are a set of slaves and a master, or a set of nodes communicating among each other, they would negotiate to have one identified as a master, and master communicate with slave by polling. So, basically the polling takes place according to a specific rule. The most common polling can be round robin, okay. So, because one after another we go, and I have the master therefore implements a round robin polling scheme, okay. And this is what is known as time division duple. When a master is transmitting, slave is receiving and cannot transmit, and when the slave is asked for, slave will transmit, master receives, okay. So, it is a time division duple. I hope you have understood why it is a duple, because a typical time slot is provided for one-way communication, but the link actually is a two-way link, fine. So, this is time division duple, and the master determines which slave will communicate when. In fact, how does the polling takes place? Basically, master sends the request to the slave, and once slave receives the request, in the next time slot, slave will send its data. Okay. So, what we say is that alternate transmission. Conceptually, we are having alternate transmission. Master transmits maybe on even numbered slots and slave transmits on odd numbered slots. A slave can transmit only if the master has just transmitted to this slave. A slave can transmit only if the master has just transmitted to the slave. This is basically the polling mechanism. I said that communication takes place by polling, so this is the polling mechanism. So you can realize that in this context you really cannot have a conflict, because there is only one master and you have the slaves, and slaves are being provided with the slots. And if you look into the diagram, what is being shown is that this master is sending it here, slave is sending it here, and there is this frequency hopping which is taking place. The frequency hopping is taking place because each frequency occupies a fixed time period. Okay. So this is an illustration of what is meant by frequency hopping, and the frequency hopping pattern is same for the piconet. Okay. So your master as well as a slave. So if you have master with Fk, the slave at Fk plus 1, and again master goes into Fk plus 2. Okay. So Fk is the frequency used in slot K according to the hopping sequence peculiar to that of the piconet. Now the physical links can be of two types. One is called synchronous connection oriented link, another is asynchronous connectionless link. Typically the voice is transmitted through a synchronous connection oriented link. Okay. In this case, it is a time sensitive traffic. So that means we had discussed even in the last class the issues related to time sensitive traffic, because you got to have data packets arrive at fixed delay, or even if there is a variation of delay, you need to know the bound of that delay. So in this case, slots are reserved at regular intervals. If slots are reserved at regular intervals, then what is guaranteed? The arrival of time sensitive packets at fixed intervals. Okay. And so you can have therefore transfer of voice. In fact, I told you that audio transfer support has been inherent to this protocol. Okay. So that is why you have this definition of what is called synchronous connection oriented link. In fact, master can support 3 such simultaneous link, and basic unit of reservation is 2 consecutive slots, 1 in each direction. You can also understand the motivation for these. You can actually have almost like a telephonic conversation over a Bluetooth link. The asynchronous connectionless link is for best effort traffic, that is your data, and it can use variable packet size. In fact, variable packet size means the slots that will be allocated for packet transfers to support asymmetric bandwidth requirement, and only single ACL link can exist. That is the basic requirement. So the interesting feature is that these synchronous connection oriented link or asynchronous connectionless link, how they are actually created. They are actually created, if you look into it, the basic scheme is what? Actually created by reservation of slots, that is guaranteeing available of slots for delivery of time critical data. Okay. Now how does this whole process of connection establishment takes place, because that is the basic key part of your Bluetooth protocol, because you have got this Bluetooth is primarily as a ad hoc network. Okay. So devices not connected in a piconet, I had already told you, are in a standby mode. Then you have got an inquiry mode. A device sends an inquiry message to locate other devices within communication range. Okay. And that device becomes master. If the device is sending inquiry message, okay, to discover other device, then that device becomes the master. Timing and ID of other devices are sent to the master, those devices become slaves. There is also a page mode. In a page mode, master sends its timing and ID to the slaves using a page message. Now the piconet is established, because you know that master has to give its device ID to determine the frequency hopping pattern which characterizes a piconet. So in a page mode, the master sends its timing and ID to the slaves using a page message, and when it does that, a piconet is established and communication session takes place. Okay. So the basic things are, initially nodes are in standby node. If there is an isolated node, it will be typically in a standby node. Then it will initiate an inquiry, discovers the other nodes, okay, assumes the role of a master, and then goes into a page mode by which actually the piconet is set up. There are also power saving modes, because power is an important aspect of these nodes. So these are hold, sniff, park. Hold mode, no data is transmitted, and the device may connect to another piconet. So currently it's on a hold, it may decide to get connected to another piconet. Sniff is device listens to the piconet at reduced intervals. Okay. And park, the device gives up its active member address, because this active member address is what? There will be only 7 active members that can be there in a piconet, but remains synchronized to the piconet. Okay. It does not participate in the traffic, but check on broadcast messages, and that's the basic significance of the park mode. And you can realize that very easily a park node can switch to a slave mode. So this is a state diagram, so of the states in which a device is. So it is typically standby. So the legends are blue is unconnected, these are connecting states, then these are active states, and these are low power states. Okay. So from a standby mode, you typically go into an inquiry mode, okay, where you send inquiry message to discover other devices. Then there will be page mode for the master and page scan mode for the slaves. Okay. Scan mode means they are trying to process the message that has been provided by the master in a page mode, and then they go into a connected mode. Okay. And when they are connected, they will be typically in a transmit mode, when master and slaves will be normally in a transmit mode. If a slave moves out, okay, what it will go through? It will go to a hold state, which is a low power state, which is not really participating in the communication. It may go into a sniff mode, trying to find out what is happening in the piconet. It can also go to a park node. But active master and the slaves will be typically in a transmit mode. Next we have got the Bluetooth audio, because you have seen the Bluetooth audio sits directly on top of your baseband. Okay. And we have already seen that how physical link provisioning is made for transmission of time critical data like audio data. In fact, there are voice encoding schemes which are made as part of your Bluetooth. Typically you can have PCM or continuously variable slope delta modulation. This is nothing but variation of your standard delta modulation scheme. Okay. These are the two basic schemes which have been defined as part of Bluetooth protocol, and choice of the scheme is made by link manager. Okay. And negotiates most appropriate scheme for application. That means what is the encoding scheme to be adopted, that is negotiated by the link manager, and accordingly the encoding scheme is adopted for transmission of voice data. Bluetooth link also provides security. Why security is important? The moment you have got your wireless link, you can have any receiver. So you can set up an ad hoc network. I can always come into a room, put into a Bluetooth device, get connected to the network, and then listen to the messages which I am not supposed to listen. This is the basic thread in a wireless network. Fine. So security is always a very critical issue in any kind of wireless ad hoc networking. So the elements of this security, I am discussing this in the context of Bluetooth, but this is valid for various other wireless protocols as well. Authentication and encryption. Authentication is verify claimed identity. If you have a definite identity, then only you can be accommodated in a piconet, otherwise you may not be accommodated. Then there is this encryption, so use a key to encrypt the data. So even if you are listening to that data, if you don't have the key, you cannot decode that data. Okay. So associated with this would be an important problem of key management and usage, because key distribution has to take place, because these nodes need to know the key for decoding a data. So how safely the key has to be transferred, that also becomes an issue. In fact, these are very basic issues with any kind of network security protocols, and they are also relevant in the context of Bluetooth, more relevant in the context of Bluetooth, because it's a wireless channel and you can simply walk in with the Bluetooth enabled device, and since it's an ad hoc protocol, the device may try to join the group and listen to the data which it is not supposed to. Now with this kind of an ad hoc situation, what is we are getting into? We are getting into a scenario where computers have gone outdoors. In fact, we started with the basic idea of embedded systems with computers going into a variety of appliances. Now actually with the ability to have this kind of an ad hoc network, mobile network, that is your nodes joining from one piconet to another piconet, setting up your MANET in terms of your scatter net, you actually have an ability to be mobile and still stay connected. Okay, so your computer in strictly has gone into a outside world. And what you are trying to talk about now is a distributed computing in an outside physical world. Okay, distributed computing classically is in terms of computers connected. Computers were not located in a physical world, were not moving around in a physical world, but now you have that ability that computers, embedded computers, can move around, say can move around in the car, okay, and still stay connected through an ad hoc networking. So the whole idea here is cars can be collaborating for safer and more fluid traffic. You do not bother about traffic signal. Okay, you actually have communication between the cars, and you start communicating maybe when you come close together. Okay, and you know which road to take on the basis of this communication. There can be distributed object tracking over large geographical area. This is important for a variety of defense applications, and interestingly, if you know the current controversy with tracking the tiger in a variety of tiger reserves, so if you really have this kind of sensors along with computers distributed in a forest area, you can have an automatic tracking of this kind of wild animals in their habitat. So physically we are putting computers, and we have the ability to put computers in the external world and still stay connected. This leads us to what is known as networked sensing. Okay, because if you are having computers all around, what you would like to do? You would like to do sense information and communicate. So you can have now sensor nodes spread over a geographical area which performs sensing, processing, and capable of communication via this kind of wireless link. Sensors can be thermal sensor, magnetic sensor, or variety of other sensors like microphone array, ultrasonic sensors. The sensors can be static or even mobile, can be interfaced with actuators as well. So since they are interfaced with the actuators, the sensors you can control and take action influencing the environment. The next interesting thing is sensors now can be controlled. So sensors in a way are just not passive sensors. You can have formally active sensors. Okay, so sensors can be activated, aimed, directed to move, commanded to sense, process, and transmit. So it is not just the camera which is looking at me, it's a passive sensor. So now you can make that camera active in the sense that it can be commanded to move around remotely. Okay, so there can be various such sensors which can be activated, aimed, directed or commanded over your wireless link. So nodes need to coordinate their sensing, communication as well as computation tasks to accomplish high level goals. Okay, so that's what has now become reality with these enabling technologies that we have so far discussed. So what is the advantage of this kind of a scenario? You have got rapid deployment, no cabling infrastructure required. Sensor placement is close to signal sources, result in better SNR, signal to noise ratio, because you are not transmitting the signal. So environmental noise did not corrupt the data. Now we have the ability to cover wider areas. Okay, you can have variety of sampling, you can have dense sampling because you can put sensor at every spot. You can have multiple aspect and multimodal sensing. What is multimodal sensing? You can put multiple sensors, okay, put into one embedded systems, and you can have multimodality sensing. And onboard processing, because if you now put in, we have got embedded systems. So if we put a processor, so what we are talking about? The moment we are talking about the wireless connectivity sensing being put in, you are also putting a processor along with the sensor. So effectively you can process the data at the sensor itself and use low bandwidth communication link. Okay, and it will be robust against failure of small number of sensor nodes, because if you already have got an ad hoc protocol, okay, then there can be nodes discovered, nodes can move out, but you may require some special techniques to make the network self-healing, self-organizing, and ability to scale gracefully. Because if you look at, you have got local nets, and local nets are connected, okay, over shared nodes, so it can grow bigger without really putting a constraint in the resources. So effectively what we have now got is embedded sensor nets, embed numerous distributed devices to monitor and interact with the physical world. Okay, and the enabling technologies was embedded system, networking as well as the sensing schemes. In fact, sensing scheme, the most key issue is signal processing. Embedded systems, we have seen that how to have design small form factor devices, their basic characteristics. Networking is in terms of protocol, we have seen how the variety of protocols enables this kind of communication. But at the task level, at the application level, the interesting thing is that network devices can coordinate and perform higher level tasks. So there can be a distributed coordination. So today the emerging applications are many. There is home automation, okay, and in fact it is related to your environmental monitoring, habitat monitoring, precision agriculture, security, surveillance. A big housing complex, you can have a surveillance using sensor nets, okay, with the embedded sensors distributed all around. You can have agricultural monitoring, microclimate sensing. You can have habitat monitoring. I have given you an example of tiger being tracked, okay, using a sensor network. You can have water quality monitored. Okay, you can have maybe along the Jamuna you have the water flowing through, and you want to monitor pollution levels, and you want to get an automatic data acquisition that you can do through this kind of sensor nets. Then structure and equipment monitoring, because if there is an effect of earthquake, you can monitor automatically and generate the response. So you can have supply chain monitoring, because if your asset is moving around, okay, and if you can track the assets, that means any components or anything, and you can find out whether you have got enough store or not. Also you have got what is known as context aware computing. That means you can move into a room. The moment I move into this room, if I have some sensing device, okay, as well as transmitting device placed in my pocket, let's say short pocket, so the camera becomes on, the recording becomes on automatically. So a context aware system comes in. Okay, in fact, the whole area and idea of pervasive computing is built around this basic concept. Okay. Pervasive computing is what? Computing coming into everywhere, okay, and every way. So sensors can be variety of sensors, okay? Passive sensors, active sensors. Active sensors are those sensors which actually transmit some energy, and on the basis of transmitted energy, it makes sensing of the external world, okay? And the technology trend is to make these sensors as small as possible, okay? So what are the design issues that comes up in this kind of a sensor net? The basic issue is self-configuration, okay, because you cannot physically reconfigure a system because environment may change without your knowledge. The whole system should have the ability to reconfigure on its own. A node can fail arbitrarily, but a node failure should not make the failure of the entire network imminent. There should be an ability to self-healing or even notification being generated for this failure of nodes, okay? Then leverage data processing inside the network. So exploit computation near data to reduce communication, and these leads to what is called known as collaborative signal processing, okay? Collaborative signal processing means there can be multiple nodes collaborating with each other for a signal processing task, okay? And you have long-lived, unattended, untethered, low duty cycle systems, because if you put such a system in a forest, you cannot visit regularly. So you got to design them as a robust and should be battery powered, and battery is expected to last for years altogether. So energy becomes a central concern, and what is very important is communication becomes a primary consumer of energy, okay, because you have seen, you have got processors which have got very efficient energy characteristics and energy saving modes as well. But when you are communicating, you have to transmit energy. So you can understand that if I can do more processing at the node itself, the need for communication would be less. So there is this interesting duel comes up between communication and computation. How much of computation is to be done? How much of communication is to be done so that you can optimize your energy usage. Next thing comes is with the embedded control. So if a node is embedded in unattended way, so it can have a control systems. So you effectively get a control network which act in the environment, okay. So and you need critical applications which extend beyond sensing to control and actuation. So in fact, you can think in terms of a variety of control actions which can be initiated through this process. In fact, a simple control action could be that a kind of a hypothetical, slightly futuristic, you have your traffic signals sitting inside your car. At a traffic signal, what happens? Your car stops. So instead of having a traffic signal externally, you can have a traffic signal inside the car itself. So when moving through this sensing, it realizes that you should stop now, okay, and that traffic signal automatically, okay, applies a brake, because braking control can be an embedded system. We have already seen that as part of a CAN network. So your traffic signal can initiate the brake once it senses that there are other cars in the vicinity trying to cross, okay. So you can have a control mechanism built into it. The basic idea of in-network processing, the point I was telling, the communication is expensive when it's a limited power and bandwidth. So perform data processing in network, close at data, and you have a distributed data, so you have naturally a distributed communication. Now these basically leads to what is known as a collaborative signal processing task, okay. And this collaborative signal processing task takes place over space, over time. This is interesting. You should note this very carefully, because now the signal processing problem in the context takes slightly different shape. We talk about sampling of a signal over time domain. Now when a phenomena is distributed over a geographical space and you are putting the nodes at different points, what you are doing? You are doing a spatial sampling as well as temporal sampling, okay. So you are doing a spatio-temporal sampling of the signal, fine, and each sample can now be processed at different nodes? Because you are physically sampling the space by putting nodes at different locations. Okay? So, that the sample, individual sample over time gets processed at different nodes. And if you have to get the big picture out of such a network, you need to have all these nodes collaborating together. So, that leads us to the concept of what is called collaborative signal processing. Okay? So, sampling of time series from each sensor is commensurate with the signal bandwidth. Okay? And sensor field is decomposed into space-time cells to enable distributed signal processing in a collaborative fashion. I can have a uniform sampling, I can have a non-uniform sampling of the space-time. This is a simple example, okay, that of a target tracking. Fine? I can track a target using a variety of sensors. So, you see that there are various nodes and the sensors which are connected here. Okay? And let us look at a scenario. A target X moves from left to right, okay, and there are a number of activities to handle. Fine? So, this is your target, first target, which is moving along this path, and these are all nodes, and these nodes are not always communicating with each other. The blue arrow shows you that when, depending on the need, the communication is set up. So, first is the discovery of the target. The discovery of the target can be by this node A, okay, and there can be a query injected into the network by the user from here. Okay. Query could be, what is that target? Okay. There can be long term queries which are there in the network itself being processed. Now, the query processing would require what? The routing of the query to the appropriate node, because the query has been posted by some node at some point. And when there is a long running query, it requires data accumulation for servicing the long running query. Then comes the collaborative processing, because this node A has got some information and now this object is moving along. So, node B has to be alerted to gather information about this node. Okay. So, this is the basic collaborative processing. Just consider that you have got multiple cameras and there is a person moving around and you want to keep image of that person using multiple cameras, but these cameras are not taking images blindly, they are taking images when they are being activated. Okay. So, another target Y enters, so here you need to track both the targets, fine. So, you have to have a time sharing. So, all the issues of time shared concurrent systems becomes relevant with respect to the nodes that we are dealing with. Also, there is a problem of data association. The data that is being sensed, I need to know that data belongs to which object. So, that is the data association problem. So, this is a very typical example of what we call collaborative signal processing problem. And here I have basically sampled my space with various sensors. The sensors could be passive IR sensors, could be in this case example is passive IR sensors as well as your omnidirectional sound sensors, ultrasound sensors. So, a sensor node therefore would have sensors, CPU, a radio for RF communication and a battery. The battery is of limited supply. So, energy efficiency is crucial for hardware and software design. Okay. And let us look at some simple examples of such nodes. The Barclay modes, which are the most famous this kind of sensor nodes. They are modes because it says that devices that incorporate communication, processing, sensing and batteries into a small package. Okay. This Barclay mode is built around Atmel microcontroller with sensors and a communication unit. Communication unit could be an RF, radio frequency, could be a laser module or could be a corner cube reflector. So, these are for optical communications. Okay. Then it can have temperature, light, humidity, pressure, magnetometer, accelerometer sensors. Okay. So, if you see the basic framework is, this is your communication architecture, okay, and this part is your Atmel, which is a microcontroller and to which you have got multiple channels of analog to digital converters to which your sensors are actually linked, okay, and this Atmel microcontroller manages the whole show. But obviously you need a OS to run here, okay. And in fact, this Barclay, they came up with a OS called Tiny OS. In fact, Tiny OS, the interesting feature of the Tiny OS is that it is a small OS. In fact, the whole idea is that OS is being provided as a set of components, okay, and your application needs to use these components, and you compile OS as well as application together. You have a high level language specification. So when you compile it together, your application along with OS gets compiled into a source code which gets loaded onto the actual mode, okay. In fact, it uses actually non-preemptive FIFO scheduling, because there is a task queue, tasks are put on the task queue, okay, and then they are scheduled for execution. When the task queue is empty, what happens? The node goes into energy saving mode. These tasks typically run to completion. When are these tasks preempted? Whenever there is an interrupt, because there are so many sensors, whenever there is an interrupt, these tasks are preempted. These interrupts are referred to as events, okay. So each interrupt corresponds to what is called an event context, okay, called an event context, okay. So this is the basic event interface which is defined via event context. And when an event context means what? An interrupt service routine which is of small duration, and it would do some small work, and again it would go back to the task. Task is not interrupted for servicing another task. In fact, the whole OS is modeled as a collection of concurrent FSM module with a single execution context. The most interesting feature of it is that why this way the whole model has been built, because you want to minimize the complexities involved, okay. The other interesting thing is that it is a compile time memory allocation. There is no provision for dynamic memory allocation. The memory allocation is done completely in the compile time. So you cannot really have malloc calloc kind of a thing when you are developing an application in Tiny OS, because that would change your memory requirements in runtime, and it would require an overhead for heap management. So that part is completely eliminated in Tiny OS. There is another hardware example. This is I wanted to show because you have got a high level processor like ARM, which we had already studied, and it is a mode coming from Intel family, okay. So it's a backbone I2C, interconnect provides power and signaling. So you have got a sensor board, main board and power board, and use them to connect via I2C configuration, okay. I2C bus we have already discussed. They also have this antenna and this ARM core with a flash and BT radio. Basically it implements or provides for Bluetooth, and the OS is again Tiny OS and provides all the features of Bluetooth management. So you can see how these nodes can be used for setting up the network. So we had studied already Bluetooth. So let's see, I can have these nodes, okay. So effectively what you generate a pico node. So it's a fixed configuration. You are tiling the space. And putting these modes. A pico node net is set up. Then you have got multiple such pico nets, and these pico nets now get connected. So you're setting up your scatter net and the complete communication framework, okay. So this way I can have the connectivity to other nets and it can go on. So it's a tiling. So it's a network creation is a tile based approach, which is the very basic fixed configuration. You can also have an irregular network where each node performs proximity search, which is basically your inquiry, okay, and then you do a master election and set up the piconet. So that's a basic negotiation and ad hocism which can be built in. So effectively I can have these kind of nodes which are irregularly distributed. They start communication through inquiry, okay. So one gets selected as a master and then others become slave, and you basically set up the piconet, fine. And this can be done at local overlapping intervals, setting up the scatter net. So basically you can see that using the Intel modes, because it has got inherent support of Bluetooth in the software itself on top of your tiny OS, as well as the hardware support for Bluetooth communication. You can use this kind of sensor nodes in an ad hoc fashion over Bluetooth network. So, you have learned about today wireless personal area network, studied Bluetooth, and got exposed to the concept of sensor networks, and we have seen how using Bluetooth we can set up a very simple sensor networks. But there will be more interesting and sophisticated algorithms for sensor nets for which are energy conscious and as well as application conscious, and there are issues related to design of such a network based applications. So, that is what we shall look at in the next lecture. Any questions?
How a connection is de-established when a node or master or slave moves out of the...
So, see basically when you establish a connection here, so a slot is allocated, okay. So, when a slave goes into a kind of a hold mode, the master would know that it is no longer participating in the communication. So, any of the other node which is in a parked node and parked mode can now switch into a slave mode.
What about if master moves out of the range of communication?
If the master, then the piconet itself is disturbed. So, the basic idea is the piconet is set up with the master in place, okay. So, until and unless all of them agrees to hand off, okay, that piconode will no longer exist, the master really does not move out.